So I told you in the last lecture that two problems I find it really interesting, and I asked you to do that. Unfortunately, I don't have a question paper right now. Yeah. So I think the question number 7, of course, there is a typo there. So I don't know whether you have tried for question number 7, but let me try to do it here. A be the set of rational numbers between 0, 1, and In is a sequence of finite collection of open intervals. Then show that summation n equal to 1 to infinity. This is obviously a mistake because In is given to be a finite collection. Therefore, that sum should be finite. Okay. So A is rational numbers between 0 and 1. So 0, 1 intersection Q. You know that it is countable and hence the elements in A can be listed. R1, R2, and so on. That is not of much importance here. Yeah. So what more you want, or what more is given is In is a finite collection of open intervals covering A. So I will write n is equal to, let us say, 1 to m. And it is given that A is contained in union n varies from 1 to m. Okay. And what you are supposed to prove is that length sum to at least to 1. Summation n is equal to 1 to m L of In. Please correct that typo. Is greater than or equal to 1 to prove this. Now, first of all, is it okay to have this condition? Namely, A can be covered by finite interval. Is it possible? Can you cover set of all rational numbers between 0 and 1 with the help of finite number of open intervals?
Yes, sir.
Yes, sir.
Yeah. Of course, that will follow from compactness as well, no? In fact, every open cover has a
Finite
finite
subcover.
Finite subcover.
even for whole 0, 1. Therefore, in particular for rational numbers. Okay. So let the rational numbers be something like this. I cannot order them according to the increasing or decreasing order, but I can list them. R1, R2, R3, and so on. And you have finitely many open intervals covering these rational numbers. Okay. Intentionally, I draw with a gap. But we have to see whether such gaps can happen or not. What you have to prove is that summation length of In is greater than or equal to 1. But if you can prove that this finite number of open intervals that covers A can cover 0, 1 as well. Suppose you can prove this. Okay. If 0, 1 is contained in union n is equal to 1 to m, then we are done. Do you agree?
Yes, sir.
Because m star of 0, 1 is 1, the length, and this is countable additivity you can use, subadditivity. Then m star of union n is equal to 1 to m In is greater than or equal to 1. Okay. ButIns are intervals, and how do you get length then? Somehow I want to get, what we want is summation length of In is greater than or equal to 1. So can I say m star will be equal to summation length In? Yes, because Ins are measurable. Yes or no?
Yes, sir.
Therefore, m star of union will be exactly equal to sum of m stars, provided Ins are disjoint. Whether Ins are disjoint is given?
No, sir.
No, sir.
No. So how do
No,
then
sir.
I do this? Yeah. How do I do
By
this?
subadditivity, sir, we can write.
Pardon? You can write it, right? Disjoint union. If any union is given, you can write it as a.
Disjoint union.
So I would just say that it is enough to prove 0, 1 is contained in union EN. Okay. The reason follows from the fact that M star is, then M star of this will be greater than or equal to 1. That is, length of L of IN will be greater than or equal to.
About some elements.
Pardon?
Disjoint union of intervals will leave out some elements in the set.
Will leave some elements. Yeah, that is true. That's true. So that's why I cannot say exactly equal, right? So somehow, that's why I rubbed it. Now I wanted to see whether this statement is correct. If 0, 1 is contained in union n equal to 1 to M IN, then we are done. That's what I thought, but let us see. Is it correct? Suppose I could prove this, then what I can say is M star of 0, 1 is less than or equal to M star of union IN, and M star of union IN, somehow I cannot write summation length of IN. That I cannot do.
Sir, by subadditivity, we can
Yes,
write.
sir.
Subadditivity less than or equal to only you will get. No, let me see.
Yes.
So M star of 0, 1, then M star of 0, 1 will be less than or equal to M star of union n equal to 1 to M IN. Okay. So that will be less than or equal to summation n is equal to 1 to M star of IN. So measurability is not needed for this. Yes, that's obvious. N is equal to 1 to M star of IN being length is L of IN. So disjointness, measurability, nothing is needed. We can work in outer measure itself. And this is 1. So 1 is equal to this. Therefore, summation n is equal to 1 to M L of IN is greater than or equal to 1. So what we observed is that the given problem, summation n is equal to 1 to M L of IN greater than or equal to 1, can be tackled if we can prove that 0, 1 is contained in union n equal to 1 to M IN. That's our observation. Okay.
Sir,
Yes.
sir, by monotonicity, we can't say summation 1 to infinity L of IN is greater than
There
summation.
is no infinity here. First of all, there is no infinity here. Where is the issue? Tell me. In the steps that I have written, I am justifying the each step, right? One, first of all, monotonicity. 0, 1 is contained in union IN will give me M star of 0, 1 is less than or equal to M star of this. That is monotonicity. In the next step, M star of union is less than or equal to summation M star. There I am using countable subadditivity. And the next step, I am using INs are interval, so M star is equal to length. So where is the issue? Tell me. Here, monotonicity. Here, countable subadditivity. And here, length and M star will coincide. Is it clear? Still you feel that there is some issue?
No, sir, it is clear. Sir, I am telling about the question summation n equals to 1 to infinity. Uh,
That I told, it is a mistake I told, right? It's a typo.
yes, sir.
Now?
So what I am telling ki, isn't it right if we take if we use monotonicity here, summation n equals to 1 to infinity is greater than equals to.
Not infinity. Don't count infinity. It is a mistake, first of all. N equal to 1
Okay,
to
sir.
M. Because A is given to be covered by, I'm sorry, I'm not getting your point. First of all, let me tell you some points from this side. Then you can, if it is not satisfying your query, then you can ask. First of all, IN is given to be a finite collection. Therefore, I am saying in the question there is a typo. It should be summation n is equal to 1 to some finite number m, length of in greater than or equal to 1. All of you first make that correction in the question paper. It should be n equal to 1 to m, length of in. Okay. Now you can proceed, whoever has asked. Are you giving me some other approach? You can use monotonicity, you are saying.
No, sir.
Huh?
No, sir.
So then tell me, what I'm not getting you, what exactly you wanted to express.
Sir, here it is a finite collection. So, sir,
It's a finite.
can we take countably finite? That's what I'm saying.
I don't understand. There is a finite collection. Can I take?
Countably finite. Sorry, sir. Sorry, sir.
Somehow I am not able to get you. If it is finite, it is countable, right? Countable means what? Finite or denumerable? And
Yes.
is it that your question countable subadditivity can be applied here or not? Obviously, you can apply the remaining, you can take it as null set. Once something is true for infinite sum, it will be true for finite sum because you take the other things as 0. In the context of set, you take it as null set. I don't get your question still.
Sir, it is clear, sir.
No, it is not clear to me. So you have asked a question, so you should make it clear to me first. It may be clear to you, but first of all, tell me what was your question and how it is clear.
Sir, he is saying that here there are finite set. In case of infinite set, what can we say about that?
In case of which is infinite set?
A collection of intervals covering
First of all,
rational.
that is not infinite, right? The question itself is not infinite. It handle only the finite thing. I don't know. Sorry. There is some communication gap between us. First of all, as an M.sc mathematics student, you should try to speak precisely, especially when you speak mathematics. Okay. Anyway, so do you agree that if I can prove 0, 1 is contained in union n equal to 1 to m in, then I am done with the problem? That part you agree, all of you?
Yes, sir.
The reason being
Yes, sir.
written inside the brackets. Okay, the reasons is inside in the black. I have written in the bracket. So once you can prove 0, 1 is contained in, what is given to you is only A is contained in. Please see the difference. Given to you is A is contained in union n equal to 1 to m in. Using that, if I can prove that entire 0, 1 is contained in union n equal to 1 to m in, then I am done. That do you agree?
Yes, sir.
So now
Yes.
can we concentrate on that? 0, 1 is contained in union. So what it tells? What is given to you is only that A can be covered. But what I am saying is once A is covered by this, you cannot miss any real number between 0 and 1. That cover will automatically contain all elements in 0, 1, not just rational number. Of course, it will follow from density. Now let me give you an argument via this picture. Okay. Suppose this is not happening. Suppose 0, 1 is not contained in union in, but of course A is contained in union in. What does it mean? There exists at least one real number x in 0, 1 such that x is not in any of this in. Do you agree?
Yes, sir.
If 0, 1 is not contained in, so let me write, if 0, 1 is not contained in union in, that means you can find a real number. There exists x in 0, 1, that x cannot be rational because you already told that every rationals in 0, 1 is contained in. Okay. There exists x in 0, 1, x not in Q, such that x is not in In for any n. For any n. Okay. I think a picture will be suggestive. So you have this 0, 1 here. You have rational numbers here. It is dense, so I should not put gap like this, but okay. Now you can cover this rational number with finite number of interval, but you are saying that there is an x which is not covered by any of these intervals. Once that is the case, you can always find nearest. You are having only finite number of open intervals, remember. So you can always find nearest left endpoint, let us say, of the open interval from x. Can you? X is fixed now, you have an x. Now from x, you can get which left endpoint of this interval is the nearest. Can you do it or not? Remember, you have only finite number of intervals. Is the question clear? Yes or no? What I'm saying is, then you can find nearest left endpoint, let us say A of the intervals, because you have only finite intervals in hand, you have to just find the distance from each of the left hand point of this and take whichever is close to x of the interval I1, I2, and so on, In. Do you agree with this?
Yes, sir.
So now let us
Yes.
say in the diagram, let us say this is the thing. A is this. Okay. This is one of the INs, and nearest left hand point is this. Now you consider XA, interval XA. Will it contain any rational number? Consider the open interval.
Definitely many.
There will be denseness, no? Then between X and A, there will be rationals. Whether this rational is coming inside some of the INs?
No, sir.
Because of your choice. A is the nearest left hand point. So these rational numbers will be mixed in I1, I2, I3, etc. Okay. And there will then between X and A, there will be rationals. There will be rationals, and these rationals are not covered by INs. N is equal to 1, 2, 3, etc. up to n. Is it not a contradiction that every rational number in 0, 1 is A is contained in union IN?
Yes, sir. Contract.
Yes,
This
sir.
is a contradiction. This is a contradiction. So what does it mean? That means once these finite number of open interval cover up all the rational, automatically it cover up all the numbers between 0 and 1. It cannot miss some real numbers. This is a contradiction. Therefore,
This might not always be the case.
pardon?
So we can have x as an endpoint of both the intervals.
I don't understand you.
So we can have x as the endpoint of both the intervals, before it and after it. Then x will be left out, since it is an open interval.
Yes, these are open interval. Yes. So are you
Sir,
saying that this will not happen?
sir, it might not happen, sir, if x is endpoint of both the intervals, before it and after it.
I don't get the exact point, but let me just think over it.
Sir, I'm saying if sir x cannot be included, sir, if x is the right hand point of the interval before it and left hand point of the interval after it,
Then
x will be left out.
so you are saying that there can exist a finite number of open intervals which can cover rationals and which can
Leave
omit,
out finitely many irrationals.
it can omit some
Irrational. Some
some
irrationals.
that is possible. That's what you are saying.
Yes, sir. If we have irrationals as the end point of the intervals. So for instance, we can take 0 comma x and x comma 1.
Mhm.
Then x will be left out.
But how do you know that then that will cover all the rationals?
Sir, take X irrational.
Sir,
Take x to be irrational. Okay, let us say some irrational number between 0 and 1. Yeah.
sir, if alpha 1 is any number less than 0, then alpha 1 comma x is an open interval, and take beta be any number greater than 1, then x comma beta. Then this covers the whole interval 0 1, but x is not included in.
So I need some time to think. I need some time. So my argument is wrong. That's what you are saying. So then how do we prove that? But I think we can prove 0 1 is contained in union n equal to 1 to I. Let me think of. So where is the issue comes? If all these endpoints are rational, then there is nothing. Then the problem is solved, right?
Yes, sir.
But can we make like that? Suppose you can cover it with open intervals. Can you cover it with open intervals of rational endpoints? Somehow by using density. So I should admit that I'm a bit confused now. I was confident about the argument, but somehow when you told, I'm not able to think right now. I'm not that fast in thinking. I have to sit and write the details, and then it will come to me. So I to be honest, I'm not getting how to tackle this. Now, whether somebody has solved this problem in any manner, forget about the argument that I have given. Especially those who have given some suggestion now. Did you solve this problem?
Yes, sir. I tried it.
You tried it. So what is your
Yes, sir.
approach?
So first I arrange the intervals
Slow.
in accordance with their
See,
infimums.
this is an online meeting, so it is very difficult to get what you are saying if you go fast. Yes. And we
Sir,
don't
if
have a provision to, I don't have a provision to see it again. I don't want to do that. Now itself, I want to clear it. Yeah. So what was,
I arrange the intervals in accordance with their infimums.
arrange the intervals according to the infimum of what?
Infimum of the interval. Infimum I1 is less than infimum I2. If I1, I2, IN are the intervals.
Hmm.
Then I made an observation that infimum of IN will be less than equal to IN plus 1. That is trivially true, but supremum of IN plus 1, no, sorry, supremum of IN minus 1 will be greater than equal to infimum IN. Suppose
Okay.
if I1 and I2 are
No,
two
I
intervals.
didn't get the technical detail, but forget about it. You progress. So now you are comparing the supremum and infimums of the intervals involved in this cover. That's what I understand.
Yes, sir, you used this technique in one of the proofs.
So once I have, I can compare the infimum and supremum. What is the advantage? What's next? Yes. Have you written down your proof or your argument?
Yes, sir.
I don't see it completely. What you are saying is you are arranging this finite number of interval in terms of infimum of each of this interval. And what next you are saying is you are comparing the infimum and supremum of two intervals and whatever it is. After that, I am trying to get an overall picture. Yes. What is next?
Then I'm summing the lengths of all the intervals.
Okay.
Then I'm arranging them in such a manner I cannot explain it right now.
So okay,
I've
anyway,
written it down.
you write your solution and please send to me. Let me have a look into it. Okay. So for the time being, I will withdraw from this argument, since you told that, in fact, the counter example, what you are taking is if the endpoint is irrational, it will create an issue. That's what you are saying. So let me see how to fix this problem. Right now, I don't have any.
Sir,
Yes. You have some
sir,
comment?
can we do this problem by taking closure both sides?
Closure of what?
Like sir, A equal to Q intersection 0, 1 contained in union of IN.
Be slow. A is equal to
A equal to Q intersection 0, 1
Q intersection 0, 1. That's the definition. Yeah.
contained in union of N equal to 1 to M IN.
Okay.
Sir, then closure of Q intersection 0, 1 is 0, 1.
Okay.
Contained in closure of IN, union of IN.
A closure will be contained in closure of union I is equal to 1 to M IN. Okay.
Sir, closure of union N equal to Y to N IN equal to union of IN closure.
That I have to check. Okay. Proceed. A union B, the whole closure is A closure union B closure.
Yes, sir.
Okay. Okay. Let me agree. Okay. Then, so if you want, I can write it. What you are saying is this: A is contained in union I is equal to 1 to M, where A is actually 0, 1 intersection Q. Take the closure, inclusion will be set same. Union I is equal to 1 to M II.
II closure.
That is union I is equal to 1 to M II closure. Okay.
Sir, now M star of A closure will be 0, 1. Interval 0.
That's okay. M star of A is less than or equal to summation I is equal to 1 to M star of II closure. Closure and II doesn't matter. Length, it will be length only. Summation I is equal to 1 to M length of II. So what?
Sir, M star of A closure is 1.
That is okay. Yeah, that's okay. This is 1. Less than or equal to. So what?
So, sir, proved.
It is supposed to be.
A is contained in I is equal to 1 to M II. Okay. So a closure is this, where this closure has helped us. So a closure is this. Okay.
That A closure is 0, 1 close interval. Then M star of A closure is 1.
Oh, okay. This is where it helped. This is where
Yes,
it helped, right? Yeah. Yeah, I think this is enough. Yeah. You are right. Who has told this?
Sita.
Sita. Yeah, I agree with that. So what is the advantage is that you can get M star of A closure, because A closure is the full 0, 1, right? That's why you are taking closure. Yes or no?
Yes, sir.
Yeah. A has M star to be 0. Because it is countable, M star will be 0. So that will not help us. But when you take A closure, you will get A closure to be 0, 1. Therefore, M star. So, okay. So let me just rub all these things and try to write it once again. I don't know why I tried with X. That I will definitely try on. Maybe some hint is given in the book. Maybe that's the reason. This is one problem from D. Barra, our one of the references. Okay, measure theory and integration by D. Barra, and it is an exercise problem. Possibly they might have given a hint like this, and then I developed on it. I don't know. But anyway, I have to find out what is the mistake in that, how to modify it. So my claim that if set of finite number of open intervals covers all rationals in 0, 1, it will automatically cover all element in 0, 1. Is not correct. That's what you two were pointing out. Yes or no?
Yes, sir.
Yeah, that part I will think. But let me try to write this and see once again. Okay. I think it is better to take a new page. Now, A closure is 0, 1 intersection Q, the whole closure. That is 0, 1. And we have M star of A closure is length of 0, 1, which is 1. And A is given to be in union IN. N is equal to 1 to M. Therefore, A closure will be contained in union N is equal to 1 to M IN closure. And this you have verified, right? A union B, the whole closure is A closure union B closure. He left or what? Whoever has given that hint. Can you verify that? Closure of the union is equal to union of the closure. Or at least contained in is also okay for us.
Yes, sir. True.
Is that true?
Yes, sir.
Yes, sir. Very fine.
Yes, sir.
That is equal to even is it equality or inclusion?
Equality, sir.
Equality. Inclusion is okay for us. We want only this much. So now M star of A closure is contained in less than or equal to M star of, yeah, this seems to be more straightforward. IN closure. Yeah. And M star is countably additive. So summation N is equal to 1 to M star of IN closure. And that is equal to summation N is equal to 1 to M. All the closure you are taking inside 0, 1. So this will be again M star of IN, right? Length of IN. That is 1 is less than or equal to summation N is equal to 1 to M length of IN. Yeah, this is enough. This is enough. Thanks for that. Now, so I should not start giving my solution, I think. Similarly, I told you the next problem is interesting. Some denseness was there. I don't have a hard copy of the question paper. Yeah, E is a subset of an interval I such that M star E equal to 0. Then prove that E complement is dense in I. Yes. I will leave it to you. If somebody has solved, give me.
We can do it by contradiction.
Okay. First of all, what is dense means? Question number.
Closure of this set equal to set.
Question number 8. What is given to me is E is a subset of I. M star of E is 0. I is some interval. To prove that E complement is dense in X. Okay. So yes, as you told, closure is that, but even though it may not be relevant to the problem, I would always like to see closure in a slightly different way. This is okay. Yes, you have A. Dense means A closure is equal to X. What it really means is the following.
It intersects non-trivially with every open set.
That's the way in which I would like to see the denseness. Given any X, for every X in X, and epsilon greater than 0, you can approximate this X by an element in A. Being an approximation theorist, this is how I would like to see denseness. A is said to be dense in X if every element in X you can well approximate by elements in A. Distance between X, for every X in X and epsilon greater than 0, there exists A in A depending on epsilon and X such that distance of XA is less than epsilon. Okay. This is what one of your friends told. This is same as saying that the ball with the center at X and radius epsilon intersect A. Okay, that is B X epsilon intersection A is not equal to null set. Given any element in X, I can find an element from A which is as close to X as you want. So in that sense, A gives you a representation of X. Whatever you want to do with X can be done with A in the approximation theory sense. This is something like basis in a linear algebra. What is basis? It is a representative. Whatever you want to do with the entire vector space, you can do with the basis, because basis gives you representation of the elements. Similarly here, the dense set subset gives you representation of the original metric space. And what do you mean by separable? So at least now intuitively, is it clear?
Countable dense set.
Is it clear that denseness is like a representative? So I don't have time and energy to go through the entire space. I want a part of it, and that part should represent the whole. That's what we are doing in basis also. I want a representative so that with the help of this representative, I should get the entire picture of the vector space. Something similar to that. I don't want to have entire space into consideration. I want a part of it, and from this part, I should be able to get as far as possible the complete information about the original metric space. That's what we are doing by dense subset. Okay. Now, it is well and good if the representative is small. So if this A happens to be a small set, with this small set, I can get entire information about the big space X. But if A is finite, what is A closure?
A itself.
A itself. So you cannot expect that A closure will coincide with the X. So finiteness will not work. So what is next best? If not finite, what do you want?
Countable.
Countable. That is the definition of separability. If you have a countable dense subset, you have a representative and the representative is small enough. Small in the sense countable. If you have a countable dense subset, you call such space as separable. So a metric space separable means you have a nice representative for it sitting somewhere over there. A nice representation in the sense whatever element you take from the metric space, you can approximate it with the help of these elements in the subset. And moreover, the subset is small enough. Finiteness anyway we cannot expect. That is too much to expect because you cannot coincide with the entire space if the entire space is infinite. Okay. That's why we are going for a countable dense subset and we are defining separability. Okay. Something like a finite dimensional space. If the basis number of elements is finite, we are well and good. But here finite will not work. That's why we are going for countable. Anyway, so now look, coming back to the problem, what I have to prove is this. E-closure is dense in X means whatever element I take X in X and epsilon greater than 0, open ball with the center at X and radius epsilon will intersect E complement. Okay. To prove that, for every X in E complement, for every X in, what do you want to prove? E complement is dense in I you want to prove. So for every X in I and epsilon greater than 0, the open ball, here it is interval, X minus epsilon, X plus epsilon, intersection E complement is not equal to null set. This is what we have to prove. Do you agree?
Yes, sir.
This is what we have to prove for any epsilon. Now we are in measure theory. So to prove that something is not null set, it is enough to prove that its outer measure is positive.
Yes.
Yes, sir.
So it is
Yes.
enough to prove that. It is enough to prove that, and you try that. That's it. So that's the hint. It is enough to prove that. This is how I proceeded. It is enough to prove that M star of X minus E, X plus E, that interval, intersection E complement is strictly greater than 0. Okay. And that's not hard. That's not hard. Reducing the problem is important. So given problem, we have reduced to this. To prove that E complement is dense in I, it is enough to prove that M star of X minus C, X plus C intersection E complement is greater than 0. Do you agree with that?
Yes, sir.
Yes,
Yes,
sir.
sir.
Now we will proceed with this problem. Now how to prove that M star of this is greater than 0? Okay. X minus epsilon, X plus epsilon, you can write as X minus epsilon, standard set theoretical argument which we have done so far several times. Intersection E union E complement. Everything is inside C. When I say complement, complement with respect to I. And this is equal to X minus C, X plus epsilon, X minus epsilon, X plus epsilon, intersection E, union, X minus epsilon, X plus epsilon, union, intersection E complement. These two sets. And these two sets are disjoint.
Disjoint.
These two sets are disjoint. Therefore, M star of X minus E, X plus C. In fact, I can write M of, because this is measurable. It is an interval and hence it is measurable. Is equal to M star of X minus E, X plus C. That interval, intersection E, union X minus E, X plus E, intersection E complement. M star of that. Okay. Now, so what?
E is measurable.
E is measurable, okay. So this will be equal to what?
We can use subadditivity.
Additive.
Additivity.
How did you
M
know that
star.
E is measurable? Because M star of E is 0, right? Now, why to use subadditivity? You can say that M star. Okay. So this will be M star of x minus e, x plus e, intersection e, so many brackets, plus m star of x minus e, x plus e, intersection e complement. Okay. All are e measurable, e complement measurable, intervals are measurable, and measurable sets forms a sigma algebra. Okay. And first one is 0.
Yes, sir.
Right?
Yes, sir.
So this will be m star of x minus e, x plus, not e, epsilon, intersection e complement. And what is left hand side? M star of the interval, that is 2 epsilon, right? So 2 epsilon is equal to m star of x minus epsilon, x plus epsilon, intersection e complement. And epsilon is greater than 0, so this is greater than 0. Okay. The measure of this set is positive, therefore that set cannot be empty. Okay. So I would ask you to start viewing denseness in this manner. Don't just remember A closure is equal to S. That does not give you any nice picture about what is happening. Dense means every element in the parent space can be approximated by an element in this subset. And the error of the approximation is under your control. In that way, the dense subsets are like a representation of the original space. Please start looking in that direction. Then separability definition will be quite natural. Why you want countable? Finite is not possible, so next best is countable, so we are demanding. Anyway, the next problem, a subset of R, something about symmetric difference. I think that is quite straightforward. F is given to be measurable. F is measurable. And m star of F symmetric difference G is measurable. It's not given to be measurable, but m star is given to be 0. Therefore, you can see that symmetric difference is measurable. That implies F symmetric difference G is measurable. So two things are there. F measurable, symmetric difference is measurable. What do you want to prove? G is measurable. To prove that G is measurable. Standard set theory and maybe sigma algebra property. That's it. So somehow you have to write G in terms of F and F symmetric difference G. Now, once F symmetric difference G is measurable, do you see that F minus G and G minus F are measurable?
Yes, sir.
Yes,
How
sir.
does it work?
Yes, sir.
How? What is F delta
Symmetric
G?
difference.
F delta G by
F
definition
minus
is
G minus
F
F.
minus G union
Union.
G minus F. Okay. Not because of measurability, m star of F delta G itself is 0. So m star of these two components will be 0. M star of F minus G would be 0. And m star of G minus F will also be 0. That will give you F bar G, F minus G, and G minus F are measurable. I think now we can do. You have F measurable, F minus G measurable, G minus F measurable, and so on. Somehow I have to see G is measurable. Okay. I am always finding it difficult to use set theory judiciously. So you have F here, you have G here, and what you want to write? You want to write G in terms of all these things. So how can I write G? Can somebody tell me? G is equal to
G equals to G
F
intersection
minus
F
F
union
minus
G
G.
minus F.
Can I write this G minus F union F minus? F minus G will give you G.
G intersection F.
G minus F union G intersection F.
Okay. I'm just believing you. Okay. G minus F intersect G minus F is in G but not in F. That is this. And then intersection or
No, sir, union.
union.
Union
Union G. Okay.
G.
G intersection F. That is right. Okay. And this is measurable. What about G intersection F?
G intersection F is F minus G.
G intersection F I don't know, right? So again I have to change it. This is G minus F union. This is F minus G. Am I right?
Yes, sir.
Just see, okay. Try to write it in as unions of two measurable sets. That's it. Am I right with the last statement? F minus G.
Yes, sir.
Okay. So then G is measurable. Therefore, G is measurable. Use your set theoretical idea and try to write it as union of two measurable sets. And we know all these things are measurable. F measurable, we know. F minus G measurable, we know. G minus F is measurable. No. And in between, I use that. No, I told that F delta G measurable will imply these individual things are measurable. That is not true. If a superset is measurable, that doesn't mean that a subset is measurable, right?
Yes, sir.
Yes,
Because
sir.
you have seen an example of a non-measurable set inside 0, 1. So that's not true. But F delta G has measure 0, and that will give these two sets have measure 0, and measure 0 will give measurability. And 10 is straightforward, I think. 11 is a nice problem, and that is a theorem in T-bar. Okay. So let me just check whether I have noted down the exact number. Yes, page number 36, theorem 11. Okay, 11th problem. And what it essentially says is the following. We have proved that, give me 2 minutes. Okay, given any measurable set, you can find a nice measurable set close to it. Those theorems are called regularity theorems. Yes or no?
Yes, sir.
What was that?
Yes, sir.
Given a measurable set, I can find an open set such that open set are measurable. Not only that, the difference in the measure of the difference will be less than epsilon. Then I can find a G delta set. I can find a closed set inside the given set, and I can find an F sigma set inside, and so on. Basically, it tells that essentially the measurable sets are nice measurable sets: open measurable set, closed measurable set, G delta set, F sigma set, etc. Okay, and this is in that line. 11th problem is in that line. If you remember, we started defining the outer measure using intervals. Okay, and this theorem tells you that finally we can stay up with intervals itself. Okay, instead of approximating it with the nice measurable set, open measurable set, or closed measurable set, we can in fact approximate it with the intervals itself. That is what 11th one tells you. Okay, so 1 minute. E is measurable, and there exists disjoint finite intervals I1, I2, I3, IN, etc. So E is given to you here, and you have I1, I2, I3, etc. Therefore, their union you can take. Their union, I am not taking a cover of E. So their union may give some element extra from E and something that it may leave from E. So this is my union here. Okay. So E is given to you I can find finite number of intervals I1, I2, I3, etc. In. Their union may give some more elements apart from E, and it may miss some elements from E. So what is the error? Total error is this part plus this part, right? Yes or no? We are trying to approximate E with the help of unions of intervals. But these unions of intervals brought some new elements and it missed some new elements. So what is the total error in approximation? This and this what I have shaded. Are you able to see my screen? I don't know.
Yes, sir.
Do you agree? This is the total error in approximating E by union IN. And the result says that total error can be made less than epsilon. That is symmetric difference, right? What is the shaded portion?
Symmetric difference.
Symmetric difference.
That symmetric difference outer measure can be made less than epsilon. So total error in approximating given measurable set by a finite number of open interval can be made less than epsilon. So essentially measurable sets are finite number of open intervals. That is enough. That's what it is saying. Provided the measure of the set is finite. The other theorem doesn't have that assumption. But if you want these finite intervals to be handled with a finite number of intervals, you need measure to be finite. Okay. And 12th problem is quite straightforward. I may write the solutions of a few and I may upload because this quiz is coming. I mean, the minor is coming. If you want, I can solve the other problems and post it. Okay. Only.
So we have.
Yes.
Today we have no class after this.
Oh, okay. So can I continue for some time?
Yes, sir.
So this I will anyway not.
You can.
This I will not solve anyway, okay? Because it is a theorem in D-bara, but you should understand what is the relevance of this theorem. The relevance is this. Essentially, we wanted to approximate a arbitrary, let us say, complicated measurable set with nice measurable sets. We did in class, we can do with, we observe in class that we can do with open set, we can do with closed set, we can do with F sigma set, we can do with G delta set. Now, here we are observing that we can in fact do with finite number of intervals. Remember, that was the starting point. Intervals was the starting point. Then we went up to measure. Now we are saying that measure of any set you can approximate by measure of the interval. Approximate in this sense. If you take finite number of intervals and take union, that may miss E in some part and it may give some more elements. So total error in approximating E with union IA is their symmetric difference. And that symmetric difference can be made, measure of that can be made less than epsilon. So in this sense, essentially measurable sets are finite union of open intervals. Okay. So now let me go back to 10.
So,
yes.
So intuitively, by the diagram, the epsilon has to be greater than a measure of E.
Pardon?
Actually,
no. This is for arbitrary epsilon. Whatever epsilon I am giving, you can find suitable INs such that happens. Okay. This IIs I have to find. I can find II depending upon your epsilon, and this N also will depend upon your epsilon, so that the difference can be of less than epsilon. You start with an arbitrary IA, this may not hold. You will not get measure of E union IA to be less than epsilon. I can find suitable IA approximating E in this sense. Okay. So that I will not solve because it is a theorem. I think 10th one, should I go for the 10th one? That should be easy. Whether somebody has solved. So 11th one, you refer this book. Detailed proof is given. 10th one, could somebody solve it? Should not be difficult. Apply the definition. Do you want me to do, or you have solved it?
So one part done.
You have done. Maybe
So
I can.
measurable inequality have been proved, but measurable how to show.
Okay. So let me give hints for both, at least for part A. M star of Ka, you have to prove that K times M star of A. Okay. And then you have to prove that when is A is measurable, Ka is measurable. Okay. Now, by definition, what is M star of Ka? Let me be quick here. M star of Ka is infimum of summation length of In. Ka is contained in union In. Ions are open interval. I am just applying the definition. Okay. Now, as usual, since it is infimum, something greater than that cannot be a upper bound. Sorry, lower bound. For every epsilon greater than 0, there exists sequence In such that K is contained in union In and summation length of In is less than or equal to is added because you may have to deal with the infinity also. M star of Ka plus epsilon. This we have applied several times. This follows from definition of infimum. Now, Ka is contained in union In will give you that A is contained in K inverse of union In, assuming K to be non-zero. K inverse times. And this is union N K inverse In. Dilating each interval. Okay. Therefore, M star of A is less than or equal to summation N length of K inverse In. That is summation N. This is K inverse length of In. Okay. That's equal to K inverse summation N length of In, which is known to be less than or equal to M star of Ka plus epsilon. Therefore, now you can multiply with K. K times M star of A, you have to deal with K equal to 0 case. That I don't think it is something involved. It is trivial maybe. So K times M star of A is less than or equal to M star Ka plus epsilon. That, and epsilon is arbitrary. So I can write one more step and put star. Since epsilon is arbitrary, I have M star K M star A is less than or equal to M star of K. Okay, this solves one inclusion star one. Now we have to prove the other way around so that you can claim that both are equal. But you don't have to do it independently. From this itself, can you derive M star of Ka will be less than or equal to K times M star of A? Are you getting me? Are you there?
Yes, sir.
Yeah.
Yes.
So this part is true. Now we want to prove the other way inequality. M star of Ka less than or equal to K times M star of A. Should we have an independent proof for that, or we can derive from this? This is true for any K and any A. Any K and any A. Now, keeping that in mind, can you say something? You work with K. In place of A, you work with K. And in place of K, you work with K inverse. What you will get? Replace A with Ka. This is true for any set, right? And K with K inverse. What will you get? K inverse of M star of Ka is less than or equal to M star of K inverse. A I am replacing with Ka. Okay. That is, m star of Ka is less than or equal to, this K inverse will go to the other side, K times m star of A. Okay, and this is star 2. Now you combine. Therefore, m star of Ka is equal to K times m star of A, as we expect. If you scale a set, then the measure also will be scaled. For translation, we have proved they will be same. Now the second part, that is, if A is measurable, then Ka is measurable. Suppose A is measurable, and conversely, suppose A is measurable. First, let us prove one part. What does it mean? Measurability, apply the definition. M star of any test set T is equal to M star of T in A plus T in A complement. And this is true for every test set T. Am I right?
Yes, sir.
Now, what is to be proved? To prove that Ka is measurable. That is to prove that M star of any test set S equal to M star of S intersection Ka. We want Ka to be measurable plus that part of S which is in Ka complement. So Ka acts as a good slicer. It can cut any set to 2 pieces so that measure of the total is equal to measure of the 2 pieces. Okay. This we have to prove. Okay. Now, let us take the left hand side, right hand side. We have M star of S intersection Ka plus M star of S intersection Ka complement is equal to, given any set S, can I write it as K times some set T?
K times S over K.
Yeah, I will call it ST. Okay, so I can write this M star as some the K times some set T intersection Ka plus M star of KT intersection Ka complement. Okay, what did I do? Write S as K times some T. Remember, S is a test set, it is arbitrary. Now this is M star of KT intersection Ka will be K times T intersection A. And M star of K times a set is K times M star of that set. So this will be K times M star of T intersection A. Do you agree?
Yes.
Plus
Yes, sir.
M star of KT intersection. Do you know something about Ka, the whole complement?
K times A complement.
K times A complement. This is K times A complement. Okay. Now this is K times M star of T intersection A plus, now KT intersection Ka complement is K times T intersection A complement. Then again K you can pull out by the part A. This is M star T intersection A complement. Now A is measurable. K you can take outside, and then A is measurable. So you will get this as M star of T. Yes or no? And this is M star of KT. And KT is yes. This is M star of yes. So for any set yes, you have M star of S intersection Ka plus M star of S intersection Ka complement is this. Okay. So that proves. And I think part B is similar. So I don't have to do that. 11th question I told it is a theorem, but you should understand what the theorem is about. Essentially, it tells you that any measurable set can be approximated well by finite number of open intervals. Now 12 is again very straightforward, but it should remind you something. Some results that you already know, either from set theory or from probability. Yes or no?
Yes, sir.
Yes.
Number of elements and
Yes.
probability.
But you please, I will just give a passing remark. When you learn the probability theory in the next semester, probably, I don't know, you should understand that probability is nothing but a measure. It is nothing but a measure. So you have a set, you have a sigma algebra, and you have a measure, with the only condition that measure on the whole set should be equal to 1. Then such measures are called probability. Okay. You have omega, you have a sigma algebra, and you have a measure m. Okay. And you will put measure means, you know, it is a function from sigma algebra to extended real number, so on. But you will put one condition, m of omega. You can talk about m of omega because omega will be in scriptium. Yes or no? Scriptium
Yes, sir.
is a sigma algebra.
Yes.
So it should involve null set, full set, everything. So omega is in scriptium. Therefore, you can talk about small m of omega, and that small m of omega should be 1. Then we call such a space as probability space, and m as probability measure, and scriptium as sigma algebra of events. Okay. So my passing remark is that probability is nothing but a measure. With measure of the whole set is equal to 1. That's it. Okay. So that's why I told you cannot understand probability without knowing what is measure. Okay. Anyway, now this is not only for probability. For any measurable set, you have measure of E1 union E2 is equal to measure of E1 plus measure of E2 minus measure of E1 intersection E2. If everything is finite, I can write like that. If I have to deal with infinite also, I cannot write minus. So that's why I have written in this form. Measure of E1 union E2 plus measure of E1 intersection E2 is equal to measure of E1 plus measure of E2. Okay. I don't think I have to prove it. It is very easy. Have you done it? I will give you a hint if you want. E1 and E2 are measurable. Will imply that E1 union E2 is measurable, right? And E1 intersection E2 is measurable. This you should keep in mind. That is why we are talking about M of. Without knowing something is measurable, you should not talk about M of. You can talk only about M star of. Okay. Now, M star of E1 is equal to M star of E1 intersection E2 plus M star of E1 intersection E2 complement. Will you agree?
Yes.
Yes, sir.
Yes.
Because E2 is measurable.
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 E2 is measurable.
Similarly, E1 is measurable. M star of E1, in fact, you can write M also. M star of E2. M star of E2 is equal to E2 intersection E1 plus M star of E2 intersection. I will be quick here. E1 complement. This is because E1 is measurable. Now you add these two and you proceed. You will get. Okay. Therefore, M star of E1 plus M star of E2 will be equal to M star of E1 intersection E2. That will come twice. Okay. Plus M star of E1 intersection E2 complement plus M star of E2 intersection E1 complement. Okay. Now this is equal to M star of E1 intersection E2 plus 1 M star I will take inside a bracket. M star of E1 intersection E2 plus M star of E1 intersection E2 complement plus M star of E2 intersection E1 complement. Now see what happens to the bracket. Okay. Can you predict what is bracket?
M star.
A star of E1.
This is E1. This is E2. You have this part. You have E1 intersection E2 complement. So this part, right? and then this part. So it is written as a disjoint union. Even union E2 is written as a disjoint union. That's it. Okay. So that is equal to M star of E1 intersection E2 plus M star of E1 union E2. So that finishes the 12th problem. 13th is okay. 15 I will not do. 15 is a standard thing which you can refer in any book. That is, if you have a sigma algebra, then either the sigma algebra should be finite or it should have uncountable number of elements. Can you think of a sigma algebra containing finite number of elements? Can you think of a sigma algebra containing finite number of elements?
So phi are natural numbers, rational and irrational.
Power set. You take your set to be finite. Suppose your set has n number of elements. What about the power set? How many elements are there?
Raised to n.
2
2
power.
to power.
Power set is known to be a sigma algebra, right?
Yes, sir.
Yes, sir.
Therefore, any other sigma algebra will also have finite number of elements. Power set is the maximum sigma algebra you can think of. So every sigma algebra on a finite set will contain finite number of elements. However, if the set has infinite number of elements, then any sigma algebra you think on that set, it will definitely contain uncountable number of elements. You cannot have a sigma algebra with countable number of elements defined on an infinite set. Okay. Go by contradiction. Assume that there exists a sigma algebra with countable number of elements, so that elements in that sigma algebra you can list capital A1, capital A2, capital A3, and so on. Each are sets. Try to get a contradiction using the properties of sigma algebra. Okay. I repeat, go by contradiction. Suppose there exists a sigma algebra which is countable. Let us say A1, A2, so on. Each A capital, they are sets. Okay. Now try to get a contradiction. So that finishes 15. It's a standard problem. And I know you will be checking in what are the two venues where questions can be posted. Math overflow. Right?
Yes, sir.
Math overflow, Quora, etc. If you see, this question is a standard question and you can see many threads. Okay. So 15th, I will not do. E1 and E2, that 12th I have done. Now find an open dense subset G of R with the measure of G is less than infinity. Okay. You want denseness. So I will try to catch hold of rationals. Okay. And you want open. So I will try to catch hold of intervals. Okay. So with these two, keeping these two in mind, what I will do is take rational so that you can enumerate them and let Rn be sequence of rationals, be an enumeration. Be an enumeration of Q. Okay. Now let me consider Rn minus, let us say, epsilon by, I want finally that summation to be convergent. So 2 power n plus 1 or n plus 2 you can take. Let me take n plus 2. Rn plus epsilon by 2 power n plus 2. Okay. This interval I am calling as On. Then each ONs are open intervals, so they are measurable and so on. I want an open set, right? Now you take O to be union ON. Then O is open. No doubt about it. Do you see that O will be dense?
Yes, sir.
Because O contains
Yes.
Rationals.
all rationals.
Rational.
All rationals. Okay? Then O is open and O is dense. O is dense in R. So you got an open dense subset of R. That is okay. Now what you want to prove is M of O should be less than infinity. Okay. What is M star of ON? ON is interval, right? M star will be epsilon 2 power n plus 1. Therefore, M star of O is equal to M star of union n ON, which is less than or equal to summation n M star of ON. That is less than or equal to summation n epsilon by 2 power n plus 1. Okay, something, this 2 power n plus 1 I have selected so that this will be a geometric series and I can sum it. Okay, and what will be that? Epsilon times. Anyway, this is a convergent geometric series. You can find the sum. Therefore, M star of O is less than or equal to some maybe epsilon or something times epsilon. Anyway, M star of O is finite. Yes or no?
Yes, sir.
Yes.
Yes, sir.
So we are done. Okay. So the
Yes, sir.
cat open and dense. Dense. So I need rationals. I will seek help of rational. Open I need. So I will take unions of open intervals. Okay. Now 14th question is dual of 13.
Yes, sir.
What will be complement of a dense set? It will have empty interior, right?
Yes, sir.
Complement of a dense set will have empty interior. So 14th you can solve automatically if 13 is solved. So 14th I will give this hint. Complement of a dense set has empty interior. And 15th I will leave it to you. In fact, that's a standard question which you can see in any resource. For instance, as I told, just Google it, you will get the same question with many threads for the answer. But I would request you to try yourself by contradiction. So if you have a sigma algebra, either it will have finite number of elements or it will have uncountable number of elements. You cannot think of a countable sigma algebra. Okay, with that, let me stop. Any questions regarding minor?
What can we expect in minors?
You can expect questions.
Questions.
Oh, obviously, you can expect questions in measure theory. Let me tell you that generally I don't ask state and prove type of theorems. Obviously, I don't think somebody from IIT will ask such questions. Even in physical exam, I don't ask. So definitely not in online. Okay. Most of the questions will be applications of the result proved in the class to tackle some problems. And it is very difficult to set a question paper now because the syllabus that we have covered is too small. I mean, very little only we have covered. So I don't know how to make a question paper for 30 marks, but I will try. Yeah. So be confident with the concepts, and I expect the writing to be very precise. Very precise. You cannot say this is what I meant. You are all mathematics students, so you should write rigorously to the point. Writing too much is also not needed. To the point, rigorously, you should know to write. And I would suggest those who are interested should read the book, How to Read Mathematics and How to Write Mathematics by Paul Halmos. I may not be exactly right with the title, but you can search. Okay, it's my favorite book, How to Write Mathematics, How to Talk Mathematics, not read, How to Talk Mathematics by Paul Halmos. Okay, let me stop.
Okay, sir. Thank you.